So here in European XFEL, we are exploring the possibilities to use this brilliant light source for imaging of stochastic dynamics of the matter in the microscale resolution so far. So we are using these individual pulses to image the sample. So each pulse passing through the sample is a femtosecond duration, so it's a very fast photography practically. And we can record more than 1,000,000 frames per second, and we can synchronize our cameras to that. So you can imagine some sample which is exploding. You can track in slow motion this process. But we are going farther now, especially thanks to recently granted EIC Pathfinder project called Megahertzomoscopy. So what we are going to do is to use these pulses and obtain 3D information for every individual pulse. And to do that, you know, with maybe in other facilities or laboratories, people are obtaining such 3D information using tomography. So this is a rotating sample around some axis and you record images, but we cannot at these speeds, we cannot rotate anything. Some sample have to be stable. But what we can do, thanks to this brilliant source, we can redirect, we can generate several probes and redirect them through the sample under various angles. So this will give us for single pulse exposure under different angles simultaneously. And then we repeat this at megahertz rate. So practically we record matter in motion with 3D information with very fast sampling. So up to 4.5 million frames per second. So the X-ray beam from the machine is passing through this axis, and each pulse is so intense that we can afford to take the portion of it and redirect it under different angle. And that is done via this device here, this tiny crystal. It's a diamond, what we call splitter. It operates either in transmission or reflection geometry. So using one of such devices, we take the portion of the SASE beam, so some portion of the spectrum. This beam is passed through the point at the sample plane, and then we take another crystal which is placed at different position. We find the diffraction condition and redirect another beam through it, and so on. So by this we achieve that we have set of probes which are angularly rotated around the sample for every individual pulse of the X-ray. So this is really powerful. So now we can repeat for every pulse at megahertz rate, so 1,000,000 and more pictures. And for every picture, we get 3D snapshot illuminated with ultra short illumination time. That's a femtosecond scale. So like in photography, very fast aperture. But in this case, femtosecond scale. So at this level, everything is frozen like. So every mechanical motion is frozen.
So this setup is really powerful to look at the detail of the microstructure of the material, but this is really not enough to see the dynamics inside. We have to excite the material and change the state of the material, and then we can shoot by the X-ray. Then we can take the movie on the 3D. To do this, we have to have this pump and probe laser to modulate or change the state of the material. So that's why we are now having those setup combined with this huge X-ray 3D imaging system.
So we can take very sharp images in 3D, sampled at megahertz rate, which is opening a lot of opportunities to inspect novel materials under extreme conditions, for example, or in the motion. So stochastic motions like crack propagations, we can now map in 3D. Not yet. We are we are developing this technique. So this is first the prototyping, and we have preliminary results suggesting that this is possible.